Okay, welcome back everyone. So until now we have been talking about our two types of rectifiers, half-wave rectifier and full-wave rectifier, and what are the key differences between them, what differences will occur if we use real diodes in place of ideal diodes, etc., etc., and etc. So we intuitively understand that a full wave rectifier should work better than a half wave rectifier, right? Because the half wave rectifier cannot use the negative cycle input voltage, but the full wave rectifier can. Okay, but can we show a particular number or a metric, okay, that that can show us that a full wave rectifier is performing better? Okay, so we will derive a parameter of a rectifier, or well, not of a rectifier, but in general any signal that we might wish to evaluate. Okay, and that parameter is the DC value of a signal or the average value of a signal. Okay, so this parameter is defined for periodic signals. Suppose I have a signal like this that repeats with time. Suppose I have some signal like this, etc., etc. Okay, and I want to find the average value of the signal. Okay, this is some signal voltage across time. What will be the average value of this signal? So intuitively, what average value means that suppose we take a time period, a certain time period of a signal. Suppose this is the time period t, and you can imagine that this signal is actually made of ice. Okay, this is quite a useful analogy to understand what an average value gives. All right, so if you imagine that this signal is made of ice, and if you melt down that ice, okay, you take one time period of a signal, and if you melt down the equivalent ice beneath this signal, then the water, it will be converted to water, and the water level will come to up to a certain height. Okay, will come up to a certain height. So this height is equivalent to the average value of the signal. Okay, and in case of electrical signals, we also call this value the DC value of that signal. Okay, average value and DC value mean the same thing. So well, that was the intuitive, I guess, intuitive explanation or motivation for introducing an average value. What is the mathematical definition if we want to find the average value? Well, the mathematical definition is the average value of a periodic signal. Mind it that the signal must be periodic. Okay, we can also find average values for other signals, but it will not give the interpretation that we are looking for in the case of rectifiers. Okay, so for periodic signals, the average value of a periodic signal is, we will find the, suppose if we want to find the height of this water, we will first have to find what the amount of ice that was under this signal, right? So the amount of ice will be kind of like equal to the area beneath the signal. So what we will do is, we will take the signal that we want to find the average value, Vt, and we will integrate that signal. And what will be the limit of integration? The limit of integration will be 0 to 1 time period. Okay, as we said, we will take one time period t. And so what will be the average height of that signal? Well, the average height of the signal will be, we will divide that by, we will divide this number by the time period. Okay, well, I can write it like this, 1 by t. Okay, so the average value of a periodic signal is, we will integrate that signal from integrate signal for one time period and then divide the result by the time period. The result will be our average value. So what is the average output voltage of a half wave rectifier? Okay, we want to find that, suppose. So what does the waveform of a half wave rectifier look like? Okay, suppose let's first consider for ideal diodes, an ideal half-wave rectifier. Okay, half-wave rectifier with ideal diodes. So the the output waveform of a half-wave rectifier with an ideal diode looks like this. B out. It looks like this. It goes up, goes up, then comes down. This is the positive cycle, and the negative cycle is blank, and then again for the next positive cycle, it goes on like this. Okay, so since this is for the ideal diode, the output rises as soon as the input rises. Okay, so there is no gap in this part. Okay, so if we want to find the average value of this output, then we will have to integrate for one time period. This is our one time period. Okay, this is the full time period. We have to integrate this full time period and then divide by the time period t. So suppose since this is the output, what was the input of a the rectifier? Well, the input was a sine wave, right? Suppose we had a sine wave of the form Vm sine omega t. Okay, so this was the input. As you know, this input looks like this, sort of. Okay, this input looks like this, only the positive part of the input is passing. Okay, so to find the average value, we will need to find the area between one time period. So what is the area? Let's calculate it. So to find the area, we will have, let's see, area will be area in one time period. We will have to integrate V out. This is a function of time with dt from 0 to t. Okay, so this will be equal to the area from 0 to t by 2. That means the area for the first half part. This is the t by 2 mark, t by 2. Okay, the area of the first part, V out t dt, plus the area of the second part, t by 2 to t, V out t dt. Okay, so what this basically means is that we will do this integration by parts. We will first take the first part from 0 to t by 2. We will find that area. We will find this area. Okay, and then we will again integrate from t by 2 to t and take this area. As you can see, what is the area from t by 2 to t? Is there any output in this portion? There is actually no output. So the area, since there is no output, V out t is 0 from t by 2 to t. So this part will, the area under 0 will definitely be 0. So this part will not contribute anything. Okay, so we will only have the first part. Now, what is V out t for the first part? As we know, for, well, this was our V in. For a half-wave rectifier, the output for the positive cycle is V out equals to V in. Okay, so for the positive part, we have from 0 to t by 2, V out t is equal to V in t is equal to Vm sine omega t. Okay, how did I get this? I just put in V out equals V in, and what is V in? This is V in. Okay, so if you put V out equals to V in equals to Vm sine omega t, you will get this. Simple enough. So, well, we will need to integrate this. Well, you know how to integrate a sine function. Let me do this quickly. So I will take, since Vm is a constant, this is the maximum value of the input voltage, I will take Vm out. The integral of sine omega t is minus cos omega t divided by omega, and we have to put the limit of t by 2. Okay, so one thing we need is that if the frequency of a sinusoidal signal is omega and its time period is t, then there is a relation between omega and t. The relation is omega equals to 2 pi over t. Okay, you have learned about this relation in your school and college, and also perhaps in some introductory physics courses that you might have taken after coming to BRAC. Okay, so if we put these values, we will get Vm equals to okay, I am just going to write the result, I guess. Omega minus cos omega t by 2 minus cos 0. Oh, sorry, this will be plus since there is a minus here. Yeah. Okay, now we know cos 0 equals 1, and if omega equals 2 pi over t, then omega t equals 2 pi and omega t by 2 equals pi, and cos pi equals minus 1. Okay, so I will write the things that we are using. Cos pi equals minus 1. If you put this value, then you will get here, this will be equal to Vm times 1 by omega. So cos omega t by 2 is minus 1, minus of minus 1 is plus 1, and cos 0 is 1. Okay, so this will be 2. Now we can put the value of omega. We will use this value. So putting the value, we get Vm times 1 by 2 pi over t times 2. Okay, so this is t by pi Vm. Simple enough. Okay, so this is the area. Okay, we have found the area for the curve and the output of an ideal half wave rectifier. So what will be the average value for a half wave rectifier? Sorry. Yeah. So the average value will be, let's write it like this, V average for a half wave rectifier. This will be equal to the area divided by the time period. Area by the time period t. Okay, so the area we have found, this is the area. If we put this value, we will get here this t and this t will cancel out, and the final value will be one over pi v. Okay, simple as that. So this is the average value of an ideal, average value of the output of an ideal half wave rectifier. All right. Okay, so yeah. So what will happen if we now use a real ideal half wave, a real full half wave rectifier? I mean, if the half wave rectifier is made with real diodes. Okay, so the in the case of a real diode, the output looks like this. Let me draw both the input and the output. Well, the input will look like this. This is one wave, and the output will look like this. Okay, there will be some sort of a delay, because as we saw in the previous lecture that a real diode does not turn on instantaneously at 0 voltage. Okay, you need some voltage at the input to turn on a real diode, and after that voltage threshold has been passed, then the then the real diode will turn on. So this I can write it here. Okay, like this. Okay, so this threshold for a half wave rectifier is 0.7. Let me write it in a generalized form. This is Vd naught. Okay, and the negative cycle is off like before. So for a half wave rectifier, we need to find this area. Okay, we need to find the area for a time period. Now, if we want to find the area, this problem is similar like before, but there is a catch. What is the catch? What is the equation for this graph? Okay. In the previous case, we had the equation, if the input was Vm sin omega t, this was also Vm sin omega t, because the input was equal to the output. But for a real diode, if the diode turns on, the input and output voltages are not the same, if you remember correctly. Okay, let me just skim over to what we learned. Yeah, so this was our rectifier circuit. As you see that when the output turns on, or sorry, I mean when the diode turns on, the output is one diode drop less than the input. Okay, we have to subtract one diode drop from the input, then we will get the output. All right, so we have to incorporate this in our equation. So for a real diode, the equation of this portion of the graph will be Vm sin omega t minus Vd naught. Okay, all right, simple as that. Okay, so yeah, so what will be the area under here? We can write the equation as before. The area will be integration of we have to write the output voltage. Okay, let me write that explicitly. V out t dt 0 to t, and we have to divide that by 1 by t. Okay, this will be the average value. Now there is no signal in the negative half cycle. Okay, no signal from t by 2 to t. So we can exclude that like before, and we can write it like this: 1 by t 0 to t by 2 V out t dt. Now what is V out? We found that this is V out. Okay, so we can put this value here: 1 by t 0 to t by 2 Vm sin omega t minus Vd naught dt. Okay, now there is also another catch. Okay, what is the catch? What is the graph of Vm sin omega t? Well, this is the graph of Vm sin omega t, this portion of the graph. Okay, this is the graph of Vm sin omega t. So Vm sin omega t minus Vd naught, if we subtract Vd naught from that, there will actually come a portion below the t axis, okay, below the time axis. But in the output of a rectifier, there is no such portion below the time axis. So this expression is also not completely accurate. Okay, this expression is also not completely accurate, because if we integrate this portion, we will also get a part of the signal that is under the time axis. But since Vd naught is usually very small, you know, of the order of 0.7 volt or 0.6 volt, and Vm will be large, say in power rectifiers Vm will be at the order of 200 volts, or even in normal applications we will have 10 volt or 20 volt. So we can actually neglect this part. Okay, and this, if we even include this part, this will not cause any error in our, not cause too much of an error in our calculations. Okay, but I'm just wanting to clarify that this is not the exact approximation for finding the area, exact expression for finding the area. This is an approximation. Okay, so what will be the value of this integration? The value of this integration will be, let me break it down. I'm just writing the integration part, not the 1 by t part. 2 by 2 Vm sine omega t dt and minus v d naught dt 0 to t by 2. Okay, and I have just broken apart the integrand. All right, so we have already found what this is. All right, what was the value of this? Well, the value was, we found that the value was t by pi over vm. Okay, so let's put in that value. All right, so this is t by pi over vm. Okay, minus, and what will be the value of this? Well, v d naught is a constant, so v d naught will come out, and if you integrate from 0 to t by 2, you will get v d naught times t by 2. Okay, so this is just the area. This is the value of the area, not the average value. This is the area. To find the average value now, we will have v average half wave real, half wave using real diodes. So we will have to write, we have to divide the area by t. Okay, area by t. So if you divide the above expression by t, what we will get is 1 by pi vm minus 1 by 2 vd naught. Okay, simple as that. So what is the difference from this expression from our previous expression? Well, what previously we had got this 1 by pi vm, considering ideal diodes. So for an ideal diode, there is no forward voltage drop. The forward voltage drop is 0. If we introduce an ideal diode, we will get a half vd naught amount of forward voltage drop. Okay, all right, so great. Now we can do this calculation for the full wave rectifier. Okay, so I will not go through the full wave ideal calculation. Okay, you can do that yourself. I will just show you what we will get if we form a full wave rectifier with real diodes. All right, so if we make a full wave rectifier with a real diode, the output graph will be like this. Okay, yeah, I am showing you one period. This is not two period. This is one complete period t. As you remember, for a half wave rectifier, we did not have this part. Okay, because for a half wave rectifier there is no voltage in the negative cycle, but for a full wave rectifier we have some voltage in the negative cycle. Okay, so since I have done two peaks, you might assume that I have done two time periods. This is a complete time period. In a single time period, we will have two voltage peaks. Okay, so what will be the area for this time period? For this full time period. Okay, let's write again the expression for the area. The expression for the area will be V out t dt. Okay, from 0 to t. All right. Okay, now you see that the area from 0 to t by 2 is the same as the area from t by 2 to t. Okay, these two parts have the same area. So if we just find the area of one part and then multiply the result by 2, we will get the full area. So I will write it like this: 2 times 0 to t by 2. See, I have changed the limit from t to t by 2. Now I am finding the area of half cycle, one half cycle, and then multiplying it by 2. Okay, and V out t dt. Now, what is the expression of V out t? For a half wave rectifier, what was the expression? For a half wave rectifier, the expression was this. Okay, this was the expression. Vm sine omega t. If the input was Vm sine omega t, then the output would be Vm sine omega t minus Vd naught. Why? Because there was one diode was consuming a part of the voltage. For a full wave rectifier, how many diodes will turn on? For a full wave rectifier, we will have actually 2 diodes. Okay. So for a full wave rectifier, our approximation will be V out t equals Vm sine omega t minus 2 Vd naught. Okay, because we have 2 diodes that turn on in a full wave rectifier. If I recap again, this was our full wave rectifier. Okay, you see that for in each cycle 2 diodes were turning on. Okay, so if you put this value, what will we get? Well, let me write that this is the area. Yeah, so I will get 2. I am putting it directly, 0 to t by 2 Vm sine omega t dt minus converter minus 2 Vd naught dt. Okay, all right. Now I can split the integral again like before. So I will get integration of 0 to t by 2 Vm sine omega t dt minus 0 to t by 2 to Vd naught dt. Okay, I have just split apart the integral like before. So what is the value? We have already found the first value of the first part. It was, if you remember correctly, this was 2 times t by pi Vm. Okay, and what will be the second part? Well, 2 Vd naught is a constant now, so 2 Vd naught will come outside, and integrating from 0 to t by 2 dt, this will give us t by 2. Okay, so what will be the average value now? To find the average value, this was the area. Okay, remember this was the area. To find the average value, we have to divide this area by the time period. So V average full wave using real diodes, we have area by time period, and if you substitute the value of this area here, okay, I am just writing the result. This t and this t and this t will cancel out, this 2 and this 2 will cancel out, and we have to multiply by these 2. So the final result will be, I am just writing the result, this is pretty easy to see, you will have 2 by pi Vm minus 2 Vd naught. Okay, simple as that. So what are the values that we have found until now? Let me fill up the table that we have been maintaining in the previous lecture. Okay, this was the table that we have been maintaining in the previous lecture. Okay, so for a if we use ideal diodes, okay, if we use ideal diodes, then what is V average? V average, this is using ideal diodes. Okay, so if we use ideal diodes, the values we have found are V average is 1 by pi Vm, and for a half wave rectifier, and for a full wave rectifier it will be 2 by pi Vm. Okay, all right. So if we use real diodes, P average, this is using real diodes. So the value we have found is 1 by pi Vm minus 1 by 2 Vd naught for a half wave rectifier, and for a full wave rectifier 2 by pi Vm minus 2 Vd naught. Okay. All right. So you can see that if we just consider the case of the ideal diodes, the average value of the output of a full wave rectifier is twice that of an ideal diode. Okay, it is multiplied by 2. Okay, so definitely, as we had intuitively known beforehand, that for an ideal diode, for a full wave rectifier, since the full wave rectifier is also passing the negative cycle of the input voltage, the average value of the output voltage should be greater. So it is actually greater. If we use a real diode, then it is still greater, but there is some loss. Okay, for a half wave rectifier, we have half Vd naught time amount of loss, and for a full wave rectifier, we have 2 Vd naught amount of loss. Okay, so you in your exam you might be given some voltage, like suppose I have some half wave rectifier or some full wave rectifier. I am putting some voltage like this, 5 sine omega t, etc., etc. Okay, and the voltage drop of the diode is 0.7. What will be the average value for a full wave rectifier? Okay, if you are using real diodes, what will be the average value of a full wave rectifier? Then you will just plug in the values. Here Vm will be 5. Okay, you will just plug in the values, and Vd naught will be 0.7, and this will give you the average value. Okay, so we have found all the metrics that we can use to describe and quantify the performance of rectifiers, of half wave and full wave rectifiers. One thing that you can notice here is that, well, let me see, yeah, that the aim of rectification is to produce DC. The voltages that we have been getting until now are not perfect DC. Okay, so the voltages we have been getting until now are like this. Okay, the voltages we have been getting until now are like this. If half wave rectification, this will be like this. If full wave rectification, it will be like this. This is called pulsating DC, as your Adrita Miss has said already in her lectures. Okay, this is pulsating, but this is not a perfect DC. A perfect DC signal looks like this. It will be a flat line. Okay, it will not change with time. So we need some mechanism to convert this pulsating DC to a perfect DC or a flat DC. Okay, so we have to have some mechanism to remove this pulsating behavior or filter out this pulsating behavior. Okay, so in the next few lectures we will see how to remove this pulsating behavior from the output of rectifiers. Okay, so thank you. See you later in the next lectures.